Good morning. In the last lecture, I introduced you to how to extend the flexibility approach to include statically indeterminate structures, frames, and how to solve the entire problem. Okay, so that is called as the matrix force method. And then we started looking at a particular problem. Okay, just to review the problem to you. Now let's see what were the steps. If you look at this, this was the problem that we had, that using the matrix force method you had to find out the horizontal sway of the top and find out the support reaction and membrane forces and bending moment diagram. Okay, then the way we went about it was that these were the 2 degrees of freedom which were defined, and ultimately what did you do? You went ahead and found out first and foremost the displacements, the SI0 and the VI0. Okay, once you found those out, then the next step was to find out the BI0 and BIR and the BIX. So those also we found out, BIR and BIX, okay, by doing equilibrium. Then I listed out all of these things, and ultimately this was the equation that you had to solve. Now here R was equal to this. This you can do if you just rewrite it. Okay, so this into R plus BIR into X. So this is FRR, this is FRX, this is FXR. You will find out that this, if you take the transpose of this, you will get BIR, FI transpose BIX, FI transpose is itself, and therefore you see that FXR is equal to FRX transpose, and then you can find out FIX. And these are the additional terms due to the VI. I do not have the terms for SI0 over here because in this particular problem we've already seen that SI0 is 0, and therefore I'm just dropping those terms out. So now all I need to do is evaluate all these terms and then put them into the equation. And if you look at this, the first step is to find out the summations. Now note that since Vi0 is equal to 0 excepting for I equal to 2, therefore the summation term only has these 2 terms, and I found them out. B2R transpose V20 is 312 upon EI, and B2X V20 is 625. Okay, what's the next step? The next step is to find out the various BIR and BIX, all those. Okay, so this is what we are going to go through the steps now. If you look at it, and let me just go about it. So we'll do it member by member. So first and foremost, member 1, let me find out BIR transpose. What am I doing? I'm actually evaluating. See, I've evaluated this term because this term, excepting for I equal to 2, everything else is 0. So this term is equal to 312.5 and this term is equal to 625. We've already done this. Now the next step is to find out this. Well, I don't need to find out this because it's going to be equal to this, and I'm going to find out this. Okay, so if I put that in, I get for member 1, B1R transpose F1 into B1R. So what is B1R? B1R transpose is going to be 0 5. And what is F1? L upon 6 EI. L is 5 upon 6 EI. 2 minus 1 minus 1, 2. And here we have 0, 5. So if you look at this, we're going to go through all the steps so that you know exactly how we are solving this. If I look at this particular thing, you will see that you will get 0, 5 inside minus 5 here, 10, and this is equal to 5 upon 6 EI. So you get this is equal to 250 upon 6 EI. So let us look at B1R F1 B1X. So this you will see, since BR1, you will see this, since BRIR and BIX are identical, so both will give you identical results. So you're going to have 250 upon 6 EI and B1X. This incidentally is equal to BIX transpose F1 BIR. Satisfy yourself that that is indeed the case, and B1X is also 250 upon 6i. So I have found that out for member 1. Similarly, I am going to find these for member 2 and member 3, and so for member 2 I have B2R F2 B2R, which if you look at B2R, which is minus 5 0 and into the same, all the AFIs are the same because the lengths are the same, the EIs are the same, and so here this is equal to minus 5 0, which is equal to minus 5 0 multiplied by minus 10. So if you look at this, you will have minus 5 0 into minus 10 5. So this into 5 upon 6 EI, and so this is equal to 250 upon 6 EI. Now B2R transpose F2 B2X is minus, this is going to be different because if you look at this, B2X is equal to minus 5 5. So this is going to be equal to minus 5 0 into minus 10 minus 15, and here also this is plus 15 plus 5 plus 10, 5 upon 6 EI. This is going to be equal to 375 upon 6 EI. Okay, then if we do this, by the way, is going to be the same as B2X transpose F2 B2R. So if we do B2X F2 into B2X, you will get it equal to minus 5 5 5 upon 6 EI, 2 minus 1 minus 1 2 minus 5 5. So this is equal to minus 5, 5, minus 15, minus 15, which is equal to 750 upon 6 EI. So we've done it for member 2. So now finally we have to do it for member 3, and let us see what we get for member 3. Once we've done it for all 3 members, you will see that we can add up and actually solve the problem. Okay, so let us look at B3R, F3, B3R. This is equal to B3R is equal to 0, 0, 5 upon 6 EI, 2 minus 1, minus 1, 0, 0. And without much ado, we can see that this is going to be this. Similarly, you will see that B3R F3 into B3x, even though B3x is not equal to 0, you will see since this is 0 that this is equal to this, and finally B3x transpose F3 B3x is going to be equal to minus 5, 0, 5 upon 6 EI, 2 minus 1, minus 1, 2 into minus 5, 0, and this you will see is going to be equal to 250 by 6 EI. Now, having done all of this, we need to add for each one, and when we add them, this is what we get. R equal to, now B1R, we're going to add up all of them, and so you will have 250 plus 250 plus 0, so this is equal to 500 upon 6 EI R. Note that this vector is R is just a vector of 1, and this is what you will see, that this is nothing but R1, this is nothing but R1, then plus, now BIR transpose FIX, if I add all of them up, you will see 250 plus 375 plus 0. So this is going to be equal to 250 plus 375 is equal to 625. So 625 by 6 EI x1 plus BIR 0, which if you remember was equal to 312.5. So that was positive. So plus 312.5 upon EI. And similarly x1, if you see, is equal to 625 by 6 EI x1 plus you will see 250, 250, 500 plus 750 is 1250, so it's 1250 upon 6 EI, sorry, this is R1, this is x1, plus we've got it as 625 upon EI, and so therefore we have it as 625. Now this we know is equal to 0. Okay? We know that this is equal to 0, and therefore what we have ultimately is, now do we know R1? We know R1. R1 is equal to 10. Okay? So we have 625, 6250 plus 6250, So this is going to be equal to 6875 upon 6 EI plus 1250 upon 6 AI. X1 is equal to 0, and we solve for X1. X1 is equal to minus 1250, which is equal to minus 5.5. Okay, kilonewtons. Okay, so we have X1 equal to minus 5.5, and therefore R1 is equal to 5000 upon 6 EI minus 3437.5 upon 6 EI plus 312 upon EI. So if you look at this, I'm sorry here, this is wrong. This is 6250 and plus this is wrong here. This is 6250 plus 3725. 625 into 6. 625 into 6 is equal to 6750. So 6750 is going to be 10,000. So this is going to be 10,000. This goes, so this goes 5, 25 goes 40. 8. This is minus 8 kilonewtons, and so when you do 8, you over here you get 205,000, and what you're left with is 312 upon EI. Okay. So, and that is your R1. So you know your R1, you know the sway. Okay, so you found out your sway, and ultimately, once you found out your sway, the next step is finding out the rotations, right? And if you look at the member end forces, the member end forces will be given by SI is equal to BIR plus BIXX. Okay, so let us look at S1. S1 is equal to note plus SI0. SI0 is 0 for all of them. Okay, so BIR, B1R is equal to 0, 5 into 10 plus B1X into 8. So this, if you see, will turn out to be 0, 10 kilonewton meter. S2 is equal to minus 5 0 into 10 plus minus 5 plus 5 into 8. So what we finally get, sorry, this is minus 8. So finally what we get is minus 10 minus 40, and S3 is equal to 0 0 10 minus 5 into 0 into minus 5. So I get 40 0. These are my member end moments. So if I put these in, let us see what we finally get. This is my x1, minus means in this direction, okay, and then if I take moments about this point, you will see that I get 10 into 550 plus 100, 150 divided by 5, so essentially I get this is your member end forces, and if I were to plot the bending moment diagram, it would look like this. Here this is in this fashion, here it is in this fashion, here it is in this fashion. And these are the member end moments that you already have. Okay, so this is your bending moment diagram. This one is this way, that is only due to the load, but there is a superposition over here, and that's 50. So this is going to be 10 and 40. So at the center, it is going to be equal to 40 minus 10 upon 2 is going to be 15 in the middle. So this is going to be 35. So it's going to go like this and like this. Okay. So here I have this, and over here this is going to be 35 kilonewton meter. And this is the total bending moment diagram, as well as you know what R1 is equal to. R1 is equal to 312.5 EI in this direction. Okay, that is solving this problem using the matrix force method. I suggest that you solve this problem using your standard force method and satisfy yourself that whatever answers we have gotten are the answers that you would get using the standard. I can assure you that you would get exactly the same if you went ahead and did it that way. Okay? So much for the matrix force method as used for frames. Now these are using flexural members. Now I want to spend the next bit of time looking at a problem where you have truss. In other words, the axial deformation is the key. Okay, so let us take a problem for that. Okay, this is the problem, and here the question asked of you is the following, that I need to know how much this has gone by, and I want to find out the horizontal displacement at this roller, and I also want to find out what are the member forces. Now this is again a static indeterminacy. This is a problem that we have looked at earlier. The static indeterminacy is 1, and I am going to assume that this is my x1. Okay, so the internal force is x1. So how am I going to solve this problem? Well, I am not going to go through all the details. All I am going to tell you is how am I going to set up the problem, okay, and that will give you the details of how to solve the problem. Okay, the numbers I am not going to go into. Okay, what we are going to do here is assume that this is 10. We will take this as also as 10. Okay. So therefore, let us take down the steps over here. First and foremost, what are the F, the flexibility matrix? You will see that Vi is nothing but delta I. It's just a single degree of freedom. Si is nothing but Pi, and Fi is nothing but Li upon Ea I. In this particular problem, we will assume that the EAs are the same for all the members. Okay, so then if we put it in this fashion, A, B, C, D. Let me put this member 1, member 2, member 3, member 4, member 5, member 6. Okay, so F1 is equal to F2 is equal to F3 is equal to F4, and all of them are equal to 10 upon Ea. F5 and F6 are equal to 10 root 2 upon Ea. So these are the flexibility matrices. Now what is the next step? The next step is actually to find out the equivalent statically determinate this is the hinge, this is the roller. I have this member, and this member exists, but it's cut. Okay, so therefore the force in this member is equal to 0, and we have you see, this is the point that I was trying to make, that in the force method, typically in this particular case it's very easy to solve, because you would have all the degrees of freedom. How many degrees of freedom does this structure have? You will see that this is 0. Here you will have 1, 2, 3, 4 and 5. The 5 is the only one that you've been asked to find out. You've not been asked to find out 1, 2, 3, 4. Okay. Now, in actual fact, when you actually solved it on the computer, okay, you would consider all these 5 degrees of freedom, and therefore these displacements would become joint loads. Okay. However, since I've asked you to only find out this, and this is hand calculation, I can't deal with 5 degrees of freedom plus 1, which is the 6th redundant degrees of freedom, and I would have a 6 by 6 matrix that I would have to solve. Okay. I'm not quite interested in that particular case. So if this is my only degree of freedom that I'm interested in, understand that these then become actually not joint loads, although technically they are joint loads. But in this particular case, since I'm only interested in finding this out, okay, and this out, okay, I'm going to consider these do not come as members, and so these I'm going to solve these separately, and I'm going to say that these are going to give me my SI0. Do you understand that point? Remember, I had said that you could solve it that SI to be equal to BI into R plus SI0. In this particular case, you see R is the only one corresponding to this. So this is R1 here. Okay. So therefore, and of course here in this particular case there will also be BIXX. So I am now going to club all these loads, because they don't correspond to this one, as these loads, member loads. Okay. So I can find out the member loads to begin with. So let me find out the member loads. So until and unless a joint load happens to be corresponding to a degree of freedom that you are interested in finding out, you will never consider it those loads as joint loads. You will club them together and forget about it. So I am going to just solve this problem to begin with and get my SI0 for each one. I am just going to forget it at that point of time. Okay. And therefore, so this one, let me solve for this. What am I going to get? If I take, here, this is going to be equal to 20. Okay. Then if I take moments about this point, I will get 20 into 10, 200, plus 200, 400. 400 minus divided by 10, you get 40. And this is equal to 0. Okay. So if I have this particular situation, let us go to a specific point. Since this is 0, I can find out that this is going to be equal to 20. Similarly, this is going to be equal to 20. Okay. And then what else do we have? Let's look at this particular joint. In this particular joint, they're going to be, this is going to have, the horizontal of this is going to tie up with this. So this is going to be equal to 20 root 2, and therefore this is going to be equal to 40. And if you look at this, this is going to be equal to 0. You will see that at this particular joint, 20, the vertical matches with this and the horizontal matches with this. So this is 0, this is 0. Here there is only vertical, so this horizontal is 0 and this is anyway 0. Okay? So now the point that I am trying to make is that here what do I now get? I get that S1 is equal to S10 is equal to minus 20, S20 is equal to minus 20, S30 is equal to minus 40, S40 is equal to 0, S50 is equal to 20 root 2 kilonewtons, and S60 is 0 because that happens to be the redundant force. So in other words, what I have done actually is to include all these loads as this thing, because the only one that I am interested in is here. So now next, what do I need to find out? I need to find out Ix. By the way, will there be any Vi0? There will not be any Vi0 because there are no member effects. The only time that you will get Vi0 is if you have a temperature stress or you have a lack of fit. Okay? So in this particular case there is none. So Vi0 is equal to 0, and I need to find out BIR and BIX. Okay? So BIR, how do I find out? Well, since this is the displacement, so I need to apply R1 equal to 1. Okay, and find out all the member forces just for R1 equal to 1. Obviously, this is going to give me this. You will see that this has to be equal to 0, 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 and so the only thing that you have is 1. So B1R is equal to 0, B2R is equal to 0, B3R is equal to 0, B5R is equal to 0, and B6R is equal to 0. All of them are equal to 0. The only thing that you have is B4R, which is equal to plus 1. Similarly, what you do is you find out now put x1 equal to 1. So you essentially have x1 equal to 1 and find out all the net forces. You will see that the external reactions are all 0 because there is an equal and opposite force as the internal force, right? And therefore, what you're going to have over here when you put x1 equal to 1, okay, and this is equal over here, this is going to be, if you take, this is going to be 1 over root 2. This one is going to be 1 over root 2. Then similarly over here you will see that this will be 1 over root 2, and you get this equal to 1, and you will get that this is equal to 1 over root 2. Okay? So therefore, B1 x is equal to B2x, B3x, B4x equal to 1 over root 2 minus, because they are all negative, okay, and B 5x is equal to B 6x is equal to 1. Okay, both of them are plus 1. So now I have found out my SI0, I have found out my B1R and B2R, and so now next, what is the solution? If you look at the solution, you will see that R1 is equal to summation B1R transpose BIR transpose FI BI R into R1 plus summed up BIR transpose FI BIX into X1 plus, now you will see SI0 come in, so this is going to be equal to summation over the entire BIR transpose FI SI0, okay, and X1, which by the way is what? The separation. So this is equal to 0 is equal to summation over BIX transpose FI BIR R1 plus summation BIX transpose BIX into X1 plus summation BIX transpose FI SI0. Okay, so now let me first find out these two quantities and then I'll find out these two quantities. Now let me first put down all the things on one page so that I can refer to that. My B1R they are equal to 0 and I am only left with B4R equal to 1 and then BIX, B3X, B4X are all 1 over root 2 and B5X and B6X are plus 1. That gives me my B's. Then what do I have? My SI S10 is equal to S20, which is equal to minus 20. Then I have S30 equal to minus 40. S40 is equal to 0. S50 is equal to 20 root 2 and S60 is equal to 0 kilonewton. Okay? Remember that this is identical to what I am doing. This is the problem that I had solved earlier too. Okay? The F1 equal to F2 equal to F3 equal to F4, 10 upon EA, F5 and F6 are equal to 10 root 2 upon EA. Okay? So once I have all of these things together, now all I need to do is put together the terms that I have to get, and if I put together those terms, you will see that they turn out to be equal to, these are all single terms. if you look at it in BIRR, since all the ones are 0 excepting for B4R, you will see that only B4R will contribute, and so this will become R1 will become equal to 10 upon EA R1 plus, now if you look at it, BIR, the only one that will again come in, because all the BIR transpose are equal to 0, the only one that will come in will be B4. So B4, we need to get B4x, and that is minus 1 over root 2. So this is going to be 10 into R1. This is going to be equal to minus 10 over root 2 EA x1, and then plus, now here this is the term that we need to evaluate. This is this term. Okay. Now we're going to evaluate this term. Now let me just put this together. You will see this will become minus 10 over root 2 EA into R1, and ultimately we will see that in this particular case you will see that this term, all the B4 x's are root 2, so 1 over root 2. So you will get 1/2, and 1/2 into 10 EA is going to be 5. 5 4 times is going to be 20, and then you're going to have 20, and then you're going to have 1 into 10, so it's going to be 20 root 2 upon EA into x1 plus this term. Now this term is the one that we have to sit and evaluate for each member, and let us do that for each member. Okay, so member 1. Okay, note that in all these cases BIR transpose is equal to 0 excepting for B4R. So the only one that I have to actually do is find out B for S4. But you see S4 0 is equal to 0. So you will see that summation BIR FI SI 0 for this particular case is equal to 0. Now for the BIX transpose. Now this is going to get this thing. So here I am going to do for member 1. Member 1 BIX is minus 1 over half into 10 upon EI multiplied by S10 is minus 20. So for this one, this is going to be equal to 200 upon root 2 EA. Member 2. For member 2, you will find that it's minus 1 over root 2. S2 is also the same. So for member 2 also, this is 200 over root 2 EA. Member 3. For member 3, you will see that B1, so it's 1 over root into 10 upon EA multiplied by minus 40. So you have plus 400 over root EA. Then you have member 4, and member 4 is going to have 0. S4 is 0, so this is 0. Then you have member 5. Member 5 is going to be equal to B5 is 1, and this is multiplied by 10 root 2 upon EA, and this is going to get multiplied by 20 root 2. So this is going to be equal to 400 upon EA, and for member 6 it's going to be 0. So when you add it up, you will get that summation BIX transpose FI SI is equal to 400 plus 800 root 2 all over EA. Okay. So if we come back to this particular problem, you will see that this is 0 and this is 400 plus 800 root 2 upon EA. Now what is R1? R1 in this particular case is 0. So all we get is that 20 plus 20 root 2 upon EA x1 plus 400 plus 800 root 2 upon EA is equal to 0, and R1, from this we can solve for x1 and we get R1 is equal to minus 10 upon 2 root EA into x1. And finally my SI are going to be equal to x1 plus SI 0. So you can solve for x1 in here, plug this in, you got this displacement, you know this, you substitute these and you get your member and forces solved. Okay. So what I have tried to explain to you today is how to use the matrix force method to solve statically indeterminate approach. The entire concept is built on the flexibility approach. Okay, and whether it is statically determinate or indeterminate, the approach is identical, excepting that in a statically indeterminate problem, you know all the capital R's and you don't know the displacements. You know all the loads, you don't know the displacements. For the statically indeterminate problem, you know some of the loads for which you don't know the displacements, and you don't know some of the loads which are the redundant forces for which you know the displacements, because those are the zero compatibility displacements that you have. So that's the only difference. Thank you very much. Next time onwards, I'm going to move on to the, up till now I've been looking at the flexibility approach. Next I'm going to be moving on to the stiffness approach of the method, which is also the matrix displacement method. Although we never say matrix displacement method, we call it the stiffness method. Thank you very much. See you next time. Bye.